everyone say hello so I can check the audio, please?
Hello.
Perfect. Thank you. All right, recording has started, class has started. Hi, folks. Thanks for humoring me and joining us on Zoom. By the way, whenever this sort of thing happens, you're welcome to Zoom from the room if you have nowhere else to be on campus that you can sit down and do that from. It's only the days that we're being kicked out for comprehensive exams that it would make a difference, but that's only 2 days of the semester. So I have get this thing out of the way, the course webpage up so I can make a couple of announcements. So I updated the printable version of the syllabus. So just in case you weren't aware, this page does not render very nicely when you try to print it, but I made a PDF version that does. And so every time I have a major course update, I tend to update the printable version of the syllabus as well. And the one that I wanted to point out to you is that on October 2nd, I'm going to have to be out of town unexpectedly. So I am not going to hold a regular class, but your lovely TAs have offered to step in for me and hold office hours during class time. And Vladimir is going to do that in the room, and Erica is going to do that on the Zoom. So you can all find a way. And the reason that I think that that will be useful is because homework 2 is scheduled to be due the following Monday. So I want to make sure that if you have questions that you would normally have FaceTime with us to talk about, that you'll get a chance to get those answered. Homework 1, because I had to cancel class last week, has been pushed back to Wednesday, 9/24. So assuming we get through example 2 today, that will be the due date. If not, I'll have to push it back a couple more days to make sure that we have time, at least a week or so in between classes. Oh, and by the way, I am not turning my basement into a drug den. If anyone has seen the smoke behind me, I'm running a humidifier so that I can keep talking. This humidifier actually turns different colors. So if you find yourself extra bored during class, I can turn that back on and you can watch it cycle through all the colors that it goes through. It's meant for small children to be like a nightlight, but you know, that's how I roll. So, okay. So homework has been pushed back a couple days. Class on the 2nd is turned into office hours. And that will happen, and actually, no, that won't happen again for this class. I just wanted to point out that we're having an unofficial fall break as well. So there will be no office hours for me this week. The 9th week of classes, which is the October 20th, that week, I'll be at a conference and be unavailable. So you just get a week off to catch up with things. If we're behind sufficiently to where I'm worried about it, I will leave some videos for you to watch so that we can kind of catch up asynchronously. But I'm optimistic that that won't be necessary, but we'll see. And then also, the Thursday before Thanksgiving, we are not having class as well. So if you're looking to buy plane tickets and you want to get out before they get expensive, be my guest. So you can get a head start. I have found in previous years that that particular class is never well attended for other reasons because I can think of about 5 different conferences that are happening over that period, and so people are often away for those reasons as well. So I just thought, nah, we'll do that. So, all right, those are the schedule updates I can think of. Any questions? Anything I'm forgetting?
Lisa, can you mention the GitHub website that we have now to download
Yes,
materials?
that would fall under the category of things I'm forgetting, so thank you. Vladimir has, so he had built slides last time for his formative assessment that did not render properly, but he has since fixed that problem. And he has put the slides and the files that made them on his own GitHub site. So if you're interested in learning how to use, what is it, Quarto? Is that the software? Whatever that thing does. Why would one want to learn this? Can you just give me like a 30-second explanation?
Yeah, Quarto is amazing because you can prepare different kind of materials in one platform. So if you need a Word file, HTML or PDF, you can use Quarto via VS Code or RStudio, and you will get the file you are interested in. You can use code, you can use words, images, you can create almost anything, even websites using Quarto. So I left an example, the .qmd file is the source file. If you look at that file, you will see how to create the PDF presentation. That's an example if you are interested in using Quarto. And then you have the PDF file, which is the presentation itself.
Cool. Thank you for doing that. Erica, you are not on the hook to teach Quarto if you don't want to. You're welcome to make materials, or if it would be helpful, but you don't have to as well. But Vladimir likes to do these sorts of things. I think Jonathan told me about this in the context of like making a handout that has both Stata code and R code. That's more like a markdown document to where it updates automatically. I can see that being a useful thing that I should learn someday, but that is not today. Sometimes you just got to be like, nope, that's not a today problem. So thank you for that, Vladimir. Anything else that we're forgetting? I did also I realized I was behind in listing R packages that were accumulating in the class, so I did update those to include a few more that are part of example 2 and example 3. All right, then guessing it's too early for homework questions since we haven't even gone over the example that it's about, but any homework questions for homework 1?
I do have one.
Okay.
In example 2, there was a function mentioned about unit adding or something like that. They're adding the
Unit
means.
means, yes.
Yes. And either I am blind, which is very possible, or I could not find it in a location where I could copy and paste it, or at least even look it, or even find it. And I tried to Google it, and it looked like it was your specific happy function.
Yes. It's actually not even mine, it's Jonathan's.
Okay, so Jonathan was
Yep.
kind to create a function for you, and
Yes. So yes, he taught this class in 2021, and so when he did that, he developed a couple of functions, and that's one of them. So this is the example 2 source file for R, and all of my R files are structured the same way. I load packages first, I import data and do stuff, and there should be. Where did the functions go? You're right. They're supposed to be in here.
There are 2 functions in there, but I did not see the one that you mentioned, and so
Okay.
that's
Somehow,
that's why I brought it up.
Oh.
This is not a complaint, just information.
This is the wrong class. That's why those functions are not in there. That was for the other class. Let me get your class.
I believe the function should be also in like the starter R syntax to like
Yes.
just
That's
load
what
them on.
That's where I looked, Erica, and I didn't see it in there. That's why I was confused.
Okay, yep, it is in here. So this is our class's example 2. Here are the packages. And then I have begin functions, just run this as is. And so this is the pseudo R square one, which we haven't talked
Right.
about yet, but that's coming. Total R square, and then add
Mhm.
unit means is this last one right here.
Why did I not have that?
And yes, Erica, I did try to load all the packages and functions that the homework would require into the starter syntax so that you don't have to figure that out, but they're generally going to be the same as what's in the example and possibly fewer. Okay, does that help? Yeah, you can tell which ones are his because they're written like properly, like a programmer would, and mine just sort of stack everything together. Different coding styles. I'm not a coder. Okay, we good there? All right, then let us go back to lecture 2, shall we? Would that work for folks? So we've been focusing on empty models quite a bit, talking about the idea of dividing all of the variance in an outcome into what is due to the cluster that you're in and due to what is due to which person you are. Now we get to the point where we can start adding predictors. So I want to pick up on slide 27. This is in lecture 2 for our class specifically. So level 2 predictors is what we're talking about. These are cluster specific characteristics. They're measured at the cluster level. So they would be characteristics of like the school. If you have students nested in schools, if you have students nested in teachers, they would be characteristics of the teacher or the classroom as a whole. And the good news is that with respect to regression models that you should already be familiar with, level 2 predictors work very much the same way. There's relatively little complexity. Everything works as you would expect. So in our example here, we have level 1 students nested in level 2 schools. And again, my subscripts are going to be P for person and C for cluster consistently across the semester. It just depends on the particular example what kind of P you would be. So in this case, it's student, and the kind of cluster is school. So person and student are interchangeable. Cluster and school are interchangeable as well. So we're going to be predicting language outcomes for students in schools that vary in the amount of homework that they give on average and whether they mix students from different grades together. These were variables that were in the data set. So my level 1 model looks like this. Language PC is a function of beta 0, which is going to be a cluster specific intercept, plus E, a level 1 residual for which student you are. What we have so far is what I would call an unconditional level 2 model, where unconditional means no predictors. So this is kind of like its own little empty model with respect to predicting the cluster intercept. We have a fixed intercept, this gamma 0, 0 thing. This is the mean of the cluster means. And then we have U0 as how far off the mean is for cluster C relative to what it is on average for everyone else. So U's are deviations. Together they form what the intercept should be. So this is what we've seen so far. And critically at this stage, you have all the variance in the level 2 random intercepts that is possible for these data. So this is a benchmark against which to compare further models in terms of how much variance has been explained by the level 2 predictors. So we're going to have an example model just for this set of slides here, and then I'll have a different example in example 2, where we're adding in 2 level 2 predictors. So beta 0C here has expanded, and now this looks, even though the letters are different, this looks kind of like a standard single level linear regression model in that we start with an intercept, and then we have slopes of predictors, and then we have some kind of residual deviation at the end. So how each cluster gets its own intercept in this model is some kind of starting point for what would happen when the predictors are 0, plus the effect of homework. And note that the homework variable has a C subscript, as does the mixed grade variable gets a C, because these vary over clusters only, not people. And I'm further showing that homework was on a scale where 2 was near the middle. I have no idea what these variables mean, to be honest with you. This is just an example data set that was in the Snyders and Bosker book. So I centered it at 2. So that means that the intercept here would refer to schools that give an average of 2 in homework and that do not use mixed grades, where 0 means they do not and 1 means they do. And so now we can start to see the pattern of the subscripts here. The first subscript refers to which beta the term applies to in the level 1 model. So you'll see that every subscript in this level 2 equation starts with 0, because what we're doing is creating beta 0. So that's our anchor point for what's happening at level 1 in the first subscript place. The second subscript place indexes what the order is with respect to the level 2 equation starting at 0. So this is my fixed intercept, the first term predicting beta 0. Then I have the first predictor of beta 0, the second predictor of beta 0. And can you guess what the subscript would be for the third? You can use the chat or you can talk.
3.
3, yeah. 03, 04, 05. So it goes like you would expect. And at some point, if you have more than 10, you're going to introduce some commas to keep things straight. So then it would be like 0, 10. Right, Vladimir? I've helped him write code for models that have like 22 fixed effects, and commas become your friend at that point.
I'd say go hexadecimal, you know.
Hexadecimal. Yeah, well, I'm trying to keep things a little more straightforward than that. But so yes, so the idea then is the same as what we have in a standard regression model. If this U represents the idea that we have all the variance in the intercepts that's possible, this U now is representing the idea of variance left over. So if homework and mixed grade matters in predicting average school language outcomes, then we would see that collectively the U zeros would become smaller, closer to 0, and their variance would be smaller as well. So the question is, of the total variance across clusters in their intercepts, how much is left? Now, does that idea sound kind of familiar? Like, how much variance did we start with? How much is left? What am I talking about? This is a letter question. Feel free to use the chat if you're feeling shy. What are we talking about? Variance that we had, variance that's left.
R possibly.
Yeah, we're talking about some kind of R-square type idea.
Mm-hmm.
So if you have a cluster characteristic, its main effect can only explain cluster differences. Because each of these would be constant across students from the same school, they can't possibly predict E variance. So here's what code would look like to add these level 2 predictors in SAS, Elmer, and R, and Stata and SPSS. And note that in none of these packages do you, as the user, differentiate the level that the predictor is measured at. The program figures that out. There's only one package that I'm aware of, actually there's two, that you have to specify the level. One is the HLM program and the other is MLWin. I think it works that way. I haven't used it in a number of years though, but most of the time the program will just figure that out. You don't have to do anything special to include those predictors.
Liz, I have a question.
Yeah, please hit me.
So in the previous slide, conditional level 2, yes, this one. The first one, gamma 00. Is this a predictor of? It is considered a predictor, no, right?
No, it is
Predictors are just gamma. Yes.
Yeah, it's so gamma 00 I would not consider a predictor because it's a constant that is added equally to everybody's cluster mean. I would call it's an intercept. And it is the
Okay.
intercept of the intercept specifically in this case.
Okay, that makes sense. Thank you.
Okay. Yeah, it's the jumping off point. So like if you didn't know anything else about a cluster, your best guess would be the mean. And so that's what this would take on in an unconditional model. In a conditional model, and thank you for pointing out I did not define that, conditional means like after predictors in this context. So gamma 00 is specifically now a mean for a cluster that has a 2 of homework and does not use mixed grades.
Thank you.
Yeah, thank you for the question. It's still a mean in the sense that any school that has those characteristics would have the same predicted outcome. Okay, other questions? All right, so here's an example with some numbers to it. So we're predicting language in students nested in schools, and the empty model returned an average mean of the cluster means of 41, with random intercept variance of about 18, residual variance at level 1 of about 63. So we add in our two predictors, and here's what we get. This is SAS output, by the way, but it looks pretty much the same in most packages. So our intercept has wiggled a little bit. That's to be expected because it does not mean the same thing. On the left, it's the mean of the cluster means. On the right, it is the expected language mean for a cluster with a homework of 2 who does not use mixed grades. And then from here, a slope is the change in y for a 1 unit change in x, right? That's what a slope is? Softball question. Yes, black boxes, I want to see you nodding behind there. Like, is everybody secretly nodding? A slope is the change in y for a 1 unit change in x. Okay, good, we're nodding. That's still what it is. So the only trick is making sure that you have the right verbal labels for what you're calling y, because it needs to be a little more specific. So I would not just say language, I would say school mean language as y, because that's what the level 2 model is focusing on in predicting beta 0. So for every unit more homework a school has, their school mean language would go up by 0.5 non-significantly. So homework doesn't appear to matter in this story. For mixed grades, this is a binary variable. So if you are part of a school that uses mixed grades, on average, your school mean language would be lower by about 2, and we would consider that significant. And that's it. You just have to put in school mean whatever in front of y to make that work, and talk about school this or school that as the variables. And I really would make a habit in your results section of adding the adjective as to whether this is a person thing or a cluster thing in front of all of your variables to help people keep it straight. Because as you'll see when we get to unit 3, once we get to people things, they're also going to become cluster things too. And that's where it gets very confusing, is when you have the same, what looks like the same variable in the model in 2 different spots. So to help your readers keep them straight, just getting used to this is a school thing or a student thing in this context will help them. So if we look at the variance components here, not very impressive. Residual variance didn't move very much. Do you think that's a coincidence or a consequence of our model? Residual variance is relatively untouched. Is that a coincidence or a consequence?
Coincidence?
Mm,
I don't know. You asked for input. I'm giving an input.
yeah. So those of you who've had me before, has the answer ever been coincidence when I ask that question? Never. Never. I'll just tell you that the answer is always consequence. In this case, it's a consequence of the fact that what residual variance represents is student-to-student differences in language from the same school. So adding in a predictor as to whether your school does something cannot possibly explain why I have better language than my friends, because we all go to the same school with the same characteristics. So E-variance should remain untouched. It will wiggle. Now that is always going to happen. It never will remain like exactly zero, but it will be zero-ish. I usually use a tilde in front of it, like squiggle zero, like zero-ish. Now level 2 went down a little bit, so it looks like part of the reasons why schools differed from each other in language have to do with these two predictors. So here are the verbal interpretations, what I had just said, essentially. I wanted to have those written out. The trickier part, I think, is in the model for the variance, trying to think about what these things mean. After putting in these predictors, U is a type of residual, and you will hear people call them level 2 residuals for that reason. I don't like to use that word. I call it U left over. It's the deviation of the original from the predicted school mean language for that school, where original is what it would be in the empty means random intercept model. So let me go back to the comparison of the equations, this one. So like this U is all the differences for school C relative to the mean. And this U is what remains. So we're focusing on sort of the difference in interpretation of what these are. This U doesn't understand why the schools differ from each other. This U has part of it in here, but then there's still stuff that remains. And is still the deviation of the observed outcome for person P from what their school has predicted to have. And I note again, U's and E's are values. The model parameters that we care about and keep track of are their variances. And here's the notation for those things. Okay, how we doing? Can I get a thumb check? It's a little trickier to do on Zoom, but it can happen. You have fewer gradations. Exploding thumbs. How do we do exploding thumbs? I haven't learned that one. Can someone teach me?
I don't know either.
Well, someone did it. So whoever's exploding thumbs, how did you do that magic? They don't know either. Okay, let me try. I don't know. No, I turned off the thing where it says recognize gestures because I accidentally muted myself and shut off my camera before for like no apparent reason, whatever gesture I did. Maybe when a lot of people send the same emoji, oh, it's like a crowd summary sort of deal. That would be very useful. But yeah, cool. All right, well, mostly upright thumbs. Please don't hesitate to ask questions. If you want to DM me in the chat, you don't have to put them in front of everybody. I can read them and answer them that way. And if you don't want to talk to me and would rather talk to the TAs and have them clarify something, they're happy to do that too, right? Yeah. Okay. So what if I was like, I don't want to learn multi-level modeling. Can I just do regression? Well, you can. Doesn't mean you should. For level 2 predictors, here's what you can expect to happen. So first off, you'll note that the coefficients are not the same. The only time they would be the same is if every cluster had exactly the same number of people, so it was equally weighted. So right off we get sort of the wrong summary of what the slope would be based on weighting. But then what do you notice about the standard errors across the two versions of the model without the random intercept or with? They're lots bigger once you have the random intercept in there. So it's like the model needs to understand that we have these between cluster differences, and that should be the basis of the error term beyond just the expected level 1 residual. The other thing you'll notice, this column right here, what does DF stand for?
Degrees of freedom?
Yeah, and in these models in particular, it's denominator degrees of freedom, because each of these is a 1 numerator degree of freedom test. They're a lot different too. So it looks like it's based on the number of people on the left-hand side where we don't have a random intercept, and it's based on the number of clusters on the right-hand side where we do. So then the tests themselves change as a function of these things as well. So you won't necessarily get the right answers back, even for level 2 predictors, if you ignore the fact that they are level 2 predictors and fit a single level model. Now, one alternative that I have seen folks do, and I think still do, is to aggregate up to the school level. So if you had a research question that was based only on school predictors, you didn't care about the students, they were just sort of, you got data from them just to get some outcomes. It wouldn't be completely unreasonable to aggregate up to the school level and create school mean language as an observed outcome that could then be predicted by homework and mixed grade. So it would be back to a single level analysis of schools. The problem potentially with that is that school mean language doesn't understand how it was computed. So it's being treated as a perfectly reliable outcome that does not differentiate how many students went into it. Whereas random intercepts do understand how much data goes into it, and for clusters where you don't have a lot of people, their U's are going to be closer to the fixed intercept, or what the model for the mean says, and for clusters that are highly discrepant relative to the rest of the clusters, that will be pushed into. So U's do a better job of representing school mean differences in an outcome than an observed variable would. But if you were sort of stuck for whatever reasons of model complexity or sample size, a school level aggregate analysis would be my next choice. So there's my sales pitch. A little bit about degrees of freedom. This is a very boring topic, but I just have a little bit in here. Denominator degrees of freedom are a thing in mixed models. There are multiple ways of computing them, and I have what each software package does by various things. So Satterthwaite is the one that I use in all of my examples because it is the most standard across packages. Between within is an option that is in SAS and Stata. If you use that one, then your level 2 predictors have degrees of freedom approximating your level 2 sample size. Your level 1 predictors have degrees of freedom approximating the total sample size minus level 2 minus the fixed effects. And in Satterthwaite, it works like that too, except for any predictor that has a random part to it. So if you have the intercept that has a fixed intercept and a random intercept, if you have a slope that's going to become a fixed slope and a random slope, then it's treated as a level 2 thing. So the degrees of freedom move to what it would be closer to level 2. One other that you may have heard of is Kenward-Roger. This is built into Elmer Test. It's also built into SAS, and I believe it's built into Stata as well. I'm not sure about SPSS. Oh, yes I am. There, newer versions of SPSS have it. This starts with Satterthwaite, but then it does some kind of correction to the variances based on uncertainty given smaller sample sizes. So it messes with the variances, which in turn mess with the standard errors, not just with the degrees of freedom. So it's a like another level of correction. And I will point out that this stuff really only matters in very, very small samples. So for example, a critical t-value at denominator degrees of freedom 20 would have a cutoff of 2.086. If I was like, I don't even want to use degrees of freedom, I'm just going to use a package that doesn't even pay attention, then the cutoff would be 1.96. So very few cases you would end up in between there and come to a different conclusion. And this is at 20, right? So you wouldn't tend to do a multi-level analysis with only 20 units at any level. That would be too few. So I use Satterthwaite because of its comparability across programs. KR would be another one to consider. And once you're in the world of generalized models, so adding multi-level models for binary outcomes or counts or things like that, they don't even use degrees of freedom. SAS Glimix is the only package I know of that does, that even has a choice for that. So it stops becoming a thing pretty quickly. All right, effect size. Can we talk about effect size? So just like in single level regression, you want to provide some kind of effect size that goes with your slopes. What to provide and what it means is the tricky part. There's a lot of choices. This is a whole big area of literature. One thing you can always do, regardless of what kind of model you're in, is take a t-test statistic and back translate it into either a Cohen's d effect size or a partial r. Both of these are like from the partial family, which means that it is the size of the contribution of that term relative to that term plus error. So it tells you, like, after controlling for all the other stuff, like relatively how much did this slope get of what was left. That's one option. The one that I think is probably more common in these sorts of models is what I call pseudo R-square. And this is the idea of a per variance component measure of R-square. So in the model that we're talking about, we have a level 2 variance and a level 1 variance. Therefore, we have two potential pseudo R-squares. And what you add to the model logically dictates which one should change. And so these have a very formulaic structure in terms of what should happen. They don't always behave themselves. They can go negative because of variance component estimation sort of wiggling around. So there is another way to do it, and I have papers on your reading list that I've linked here. I'll show you an example too, how to use their R package. That makes it so the pseudo R-squares say positive because it's based on model expected variance in the denominator instead. So the easier way to compute it is what's shown in the formula right here, where I have the variance component of interest in the model that has fewer parameters, so the unconditional model, for instance, minus the variance in the model that has added parameters, so the conditional model after adding the two slopes in our example, relative to what it was before. So the way that I remember this is it's was minus is over was, or 1 minus is over was, either way. And this denominator is the problem. So if you end up with adding things that really don't help the model, you could actually help make your variance go up, in which case this thing would go negative. So Reitz and Sturba figured out how to get model implied variance by essentially taking what the variance ends up being and adding back in the expected variance contribution from the predictors. So there's more computations involved in that. That's why they made R packages. I don't do that because I can't do that across packages or programs as easily. So I do this version, and this is the version that I'll ask you to do in your homework as well. Last one is total R-square. Here's the good news. You already know this one. In linear regression, if you take the predicted outcomes from your fixed slopes, like y hat, you save those as a column to your data set, and then you correlate y hat with the actual y's, that's r, and if you square that r, that's r square. So that is one of the ways in which I explain what r square means in standard regression, and that same explanation holds here. One caveat I want to mention is that it's the fixed effects only that generate these y hats. So it's a measure of your fixed slopes, not a measure of your random slopes in getting total R square. Otherwise, that would sort of be cheating. So here's some numbers to illustrate how this would play out in the example data. So in the empty model, this is what we had in language scores with an interclass correlation of 0.22. In the conditional model, we had basically the same level 1 residual variance because we haven't explained any people information. We don't have people predictors yet. And we did have a slight reduction in random intercept variance. So this is the one we care about. We added level 2 predictors, ergo, it should be level 2 variance that changes. So what it was minus what it is now divided by what it was is a 3.6% reduction in the level 2 random intercept variance. And you do have to say it that way because it is of the school mean differences. How much of that was reduced by adding in homework and mixed grade? It would not be correct to talk about this as an R square for the model of 0.036 because that would include the residual variance. So if we put this together with the intraclass correlation, of the 22% of language that was due to what school you go to, the model has explained 3.6% of the 22%. That's how you would have to think about it. It's a partition of a partition. And you can actually multiply those together. Like if you have a paper that you're reading and they don't give you a total R square, what I just did essentially is this. And I have an Excel sheet that does these computations. So less than 1% of the variance overall, as to be expected, because most of the variance was at the person level and we haven't put any person predictors in yet. So we could not have explained very much variance at this point in the exam. There. Summary. That always makes me happy when I see that header. That means we made it. So, big picture. We are taking an outcome that has multiple dimensions of sampling, and we are trying to quantify how much variance remains across each of those dimensions of sampling after adding predictors that correspond to that level. So far, we just have 2 levels in which people are nested in clusters. So we would start out with a random intercept that captures cluster differences, a residual that captures person differences, and each of those has an estimated variance. We want to know about an ICC, how much of the variance in an outcome has to do with clusters as an important statistic. That's ICC 1 in particular. And we can reduce that random intercept variance by adding level 2 predictors. And that process works pretty much the same as usual, with maybe a little bit of complication in terms of denominator degrees of freedom, but not much. And there we go. Do you want to see an example so you could do your homework? Like, yes, I would very much like to do my homework, Lisa. I thought you'd never ask. Question, Vladimir, or comment?
Yes, Lisa, I have a quick question. Well, I would like to hear something again.
Okay.
So in the empty model, the UC, the random intercept is the cluster mean deviation from the overall intercept in the model, right?
Yes.
However, once we add predictors at level 2, that random intercept becomes the difference between the cluster mean prediction and the cluster mean from the empty model.
Yes.
Okay.
Yeah, so I'm trying to get out of this. There we go. Essentially, like this U would be the same number as the U, or actually, yeah, let's say with that, it'd be the same value as the U that would result from like these 3 things. That's the idea. Is that part of what was guiding U is now being allocated to the fixed effects, but then you have the U left over.
Awesome.
Conceptually, that's the idea.
Yeah, and that's weird because we know that, well, in the way that we define random intercepts, I think that the first thing that we say is that it represents the cluster mean deviation from the fixed intercept, but that's not always the case.
Yeah, I would not say from the fixed intercept, I would say from the fixed effects in that level 2 equation.
Yes, awesome.
That's
Thank
the
you,
way I
Lisa.
would say it. Or the model for the means for that. Like the fixed effects is what the random effects are deviating from. The question is which fixed effects are in the model at that point.
Exactly. Great. Thank you.
Thank you for the question. Other questions or clarifications? Okay. I'm going to pick up then on page 6 of example 2. We have 2 more models to go. We can do it. And I haven't even had a coughing fit yet. I'm so proud of myself. I feel like I'm one of those like smooth jazz DJs though, where it's like you're listening to MLM. Straight talk. Yeah. There we go. So, do you remember this story? It's a different story. Same type of data. We have math scores that are being predicted for students within schools. That's a fairly large data set of both students and schools. And in this example, I am predicting math from the size of the school in units of per 100 students. So that's what this means. And I've centered it so that 100 is the reference. So that's essentially we started with 1,000 as the reference and divided by 10. So this is a little tricky to explain. I could probably do it that way better, but I wanted to capture the per unit idea. And then whether or not the school is public as a 0 or private as a 1. And so those variables then, I have stata output here first. C dot indicates a variable that is being treated as numeric. If you don't do that, sometimes it will default to other things, and so I've just gotten in the habit of doing that for stata. So the output then looks very much like you would expect if you've seen models in Stata for other things. Here are the two slopes, and we have our coefficient, so the estimate, standard error. So note denominator, degrees of freedom, and note that all of these are around the same. That's because the intercept is being treated as a level 2 variable when we use Satterthwaite degrees of freedom, which is what has been requested right here in that option. We have our variance of the u's that is left over. We have our variance of the e's that is still there because it hasn't been predicted. I have saved the results so that I can compute effect sizes for them. So model 2, the estimates for size, math, and then the fixed intercept. This one is going to be the random intercept variance. This one is going to be the residual variance. And I know that because they match the order in which they're given here. So down the page essentially goes across the columns in this case. So I wrote code to compute pseudo R-square for the random intercept in Stata. So I have what it is in the current model. So that's my random intercept variance left over, divided by what it was in the empty model as the baseline, and then 1 minus that. So I'm computing R-square and not the amount left over. And so it works out to be about 0.23. So 23% of the variance in math, according to this model, is related to the size of the school and whether it's public or private. So school mean math differences is what we're focusing on with that effect size. The effect size for level 1 is computed the same way, but it's one spot over in the column. And note that it's negative. That happens. Reported as 0, or 0-ish. And then last but not least, I have code here to compute total R-square. So the first step is to create a new column in the data set, that is y hat from the fixed effects. I have named that column pred main, and xb means use only the fixed effects. I've then requested a Pearson correlation between the original math outcome and the math outcomes predicted by this model. I then asked for that correlation to be squared and printed, and there it is. And then I'm going to save it as a new variable within the Stata environment so that I can get a change in R-square down the road. So in the F-test up here, Stata does this for you, R does not, but I'll show you how to do that. That is essentially analogous to the F-test of the model R-square in single-level models. It's the same idea. In this case, though, because the two slopes are specific to level 2, I would think of this also as a test specifically for the reduction in the random intercept variance. You could think of it kind of either way in this case. All right, our folks, let's look at your version. So we have size and private added as fixed slopes here. Do I want to add them inside the parentheses, our folks? Do I want to put them inside the parentheses too? Yes or no?
No,
No, we do not.
because
Inside,
with that would change that what you're finding for a condition, like that conditioned on it being a particular school ID, I think. Yes.
well, we would put it in on this side, and what
Right.
that
Oh,
would
yeah,
be
yeah,
doing,
yeah.
it would be adding a random slope, which is not really possible. So we're adding fixed slopes for our level 2 variables because there's nothing at a higher level for them to be random over. And we're not interested in heterogeneity of intercept variance in this class. So we have those two things. I'm printing out the log likelihood for the model first, and then deviance. This is your -2 log likelihood, so that's what you would put into the homework system. We have the same results with respect to random intercept variance here, which I have labeled for you, and then student level residual variance here. Let's go through and interpret things. So this will be the audience participation portion of the program. Okay, we ready? 3 numbers, we can do this. 11.18 is what? You're welcome to type, you're welcome to talk.
Gamma 00.
That's what it is. If you were going to put 11.18 in a sentence, what would that sentence sound like? Fixed intercept, yes, also true.
That would would be for a school of size 100 that is private?
Public in this case. So the
Public, sorry.
private is like the effective
Sorry,
being the one. Yeah,
okay, sorry.
either
Yeah.
way. Yeah, you got the right idea though. Yep. So that is school mean math in a school of the reference size who is a public. And then we have the effective size, which looks to be positive but non-significant. So for every 100 students, school mean math goes up by 0.06. So I would call that non-significantly positive. Other folks might just call it non-significant. And then if it is a private school, school mean math goes up by 3.15, significantly so. So for whatever reason, students are doing better in private schools. To get the same F-test that Stata provides by default, here's a way to do that. So this is a new function that I don't think you've seen either of these yet. Contest MD. So that is a linear combination, and you can do various different kinds of tests with this. In this case, what I'm doing is lumping together the two fixed slopes to get a joint F-test for their contribution. So you have to have the code as a point of reference to understand those functions. So this one right here, that refers to my fixed intercept. That's the first thing that R is keeping track of. Then we have the slope for size, and then we have the slope for private. And if you're ever uncertain as to what the order is, you can always check your output, and it should be in the order that R is storing it as. This is R's order. So in this case, I'm saying I would like the first slope, and then the comma delineates it as a separate slope, and then I want the second slope. So this is a joint test of whether both slopes are 0 at the same time. It is known as a multivariate wald test. If you're not using denominator degrees of freedom, I call it a modified version if you are. But that is how Stata got that result for the F. Question?
So if there were, say, a fourth or a fifth variable, or basically, row in there, then we would have to expand that out to like 4 or 5 or however many places to match what we have for our list underneath the fixed effects.
Yes, exactly. You have to have as many zeros and ones as you have fixed effects. It has to know what to do with all of them. And for those of you who remember intermediate or generalized with me, this is analogous to the GLHTs. It's the same type of process. It's linear combinations of things, but it's just made to work with multi-level models instead.
Do we only use zeros and ones in this test to indicate like which one you're looking at? I mean, I actually have completed the homework, but like for example, if I put a -1 in there, then
that's something
what?
different.
Yes.
Yeah, so the values that you put are completely contextual in what you're trying to do. So I think it would be easier to explain that maybe in the second example, because I've got more stuff in there for that one. But just briefly, like if I did something like this, just this much, that's asking for a difference between the two slopes. If I had a positive value, this is asking for the two slopes to be added together and tested. And then 0 means leave it out of the comparison. So this comma right here is instructing you to build one slope and then build a second slope and then test them jointly, as opposed to adding them together, which happens within the parentheses instead. So you'll see lots of little examples of these across the semester. They can be pretty useful. But there's the F value that we got. Pseudo R square, I got really tired of typing numbers in, so I made a little function. And I will put a disclaimer with my functions. I am not a coder. So my functions were written to do what I needed it to do in example 2, and once I got that right, I stopped coding. So they're not bulletproof. They don't have checks in them that stop you from doing stupid stuff. Like I don't have any of that built in. It's just a calculator. So the arguments to the function that it wants, what's your data set, what R object are you considering the base model? So in this case, it's model 1 is the empty model. And then in a very unfortunate set of names here, I decided I would name these arguments generically, and then I ended up naming my models the same thing. So my bad on that. I did not mean to be confusing. But model 2 is the name of the object that holds the model that I want to compare to the base model. So I'm going to have another set of those once we have the second model. So then it does the math for you of computing the change in each of the variance components in these two models and spitting that out. So then the output that my function generates has what was the variance in the base model, what was it in the comparison model, and then what is the pseudo R-square. So here's the pseudo R-square of 0.23 that we calculated in Stata as well, and here's the slightly negative R-square for the residual that we found there at the same time. And then Wrights and Sturba have their R-square package, which is called R2MLM. It does a lot of stuff, including make graphs that break my computer for whatever reason every time I try to run it, so I just shut that off. In this case, it's relatively straightforward because these are level 2 predictors. The only possibility is that they reduce level 2 random intercept variance. So in their papers, they have this whole set of equations and descriptions as to what these different types of R-squares mean. I would encourage you to visit that. But for our purposes, this is the one that relates to the random intercept. And so you'll note the value's a little bit different, but it's pretty close to what we computed as well. So in homework, I don't want you using this function because there's not a Stata or SAS analog that I have built. I want you using pseudo R-square. But in life, I wanted you to have seen an example of this because I think this way of doing it is probably more resilient in the long run. All right. Are we ready for one more model? Can we do it? Add an interaction term? Just to prove that we can. You know me, I love interaction terms. They're my jam. So model 3, to illustrate what it would look like to add a level 2 interaction. So I'm adding an interaction term between school size and private versus public status. And so that goes in as the third predictor of beta 0. So now we have a gamma O3 here. So this is a purely level 2 interaction because it's between two level 2 variables. There are also purely level 1 interactions possible and something known as cross-level, which we'll get to in about a month or so, where it is level 2 by level 1, but this is purely level 2. Which variance component do you think this new interaction term should target? U or E? Yeah, finger question. Yeah, U, because it's right there. So it's like this is the leftover part now after controlling for not just size and private, but also some kind of over additive or under additive interaction that this gamma O3 would create. So that means that when we talk about the effects of size and private here, we can't just say this is the slope for school size, the end. And we can't just say this is the slope for public versus private. The interaction term makes it so that each is conditional on the 0 value of the other interacting predictor. So this slope of size is specific to public schools because that's when this part would drop out. If private goes to 0, this whole thing drops out, and then the only term that's controlling the effect of size is gamma O1. Likewise, this effect of private is specific to schools with size 100 because that's the point at which the interaction term would all drop out and the slope of private would be controlled by nothing but gamma O2. So then that begs the question, well, what if you're not interested in the slope of size for public schools? What if you want it for private? Well, the same process that I taught folks before, it's the same because linear models do not change. It doesn't matter what else is in the model. To figure out what a slope is for any variable in your model, go into your equation, find all the terms that have that slope. So if I want to know the slope of size, I definitely need that term. I do not need this one because size is not in there. I do need the interaction term because size is part of that. So I carry those down. I then factor out size as a common ingredient in both, and the term that is left in front are the ingredients to how the model tells me what the slope of size would be for any kind of school. So that will show up in a programming statement to be able to get you the missing size effect for private schools beyond just what it is for public schools. So in Stata, and I'm starting to show some tricks that I deliberately hid in intro classes, pound or hashtag, take your pick. That means estimate a two-way interaction between those variables as well as their main effects. So it saves you some typing to be able to do that. So there's the new interaction term. We'll go over that in just a second. It should have reduced random intercept variance, and it did indeed. So relative to the empty model, our R-square is up to 0.237 for the random intercept, and that is a gain of about another % or so relative to the previous model. Likewise, our total R-square increased just a tiny bit. Folks using R then, I did the same kind of shortcut with respect to typing by adding in a star here. So in linear models in R, a star means estimate the two-way interaction plus the main effects without having to type them all separately. In terms of what happened, sorry, my mouse wants to scroll like way more than I want it to right now. One of the hazards of having a giant mouse, I suppose. There we go.
Mine has a button on the top that you can press to lock it, to make it not go as fast. I don't know if yours does.
I don't know. I'll have to play with that.
Okay.
Yeah. So 11.29, has that changed interpretation relative to the previous model? Yes or no? No. It's still the expected school mean math for the reference school because we haven't added any new predictor variables upon which the intercept would be conditioned. Size 100 though. Can I say that for every 100 students, school mean math goes up by 0.03?
If it's a public school.
Yeah, that's the missing piece. Mubarak, were you going to answer too? Maybe. Okay. Yeah. If it's a public school, that's the end of the sentence. So this is what we call a conditional main effect or a simple main effect. Likewise, private, this is the difference of private relative to public schools that are specifically of size 100. And then the interaction term, we can talk about two different ways. We can talk about what happens to the effective size in private schools instead of public, or we can talk about the difference between private and public and how that changes in schools of different sizes. For this example, I decided to go with the former. So the way that I would approach this is to start with this size effect. That's in public schools, right? According to the model and the interaction term, what is the size effect going to be in private schools? Stronger or weaker? One vote for stronger. 2 votes for stronger. So the answer is, do the signs match? If the signs match, it's stronger. If the signs don't match, it's weaker. I used to do a more complicated version. I would actually call this a more positive. So we have a positive slope for the effective size. That positive slope in public schools becomes more positive by 0.12 in private schools. So the interaction term tells you the slope difference as a function of the moderator. A 1 unit change in the moderator in this case is the shift across school types. I could also go the other way. This is, I would say, the private school advantage in average size schools, and that advantage grows, becomes more positive in larger schools. That's what that would mean, but non-significantly so. Boo-hoo. So then to get what the slope would be for private schools for size, I would have to add that number and that number together, right? So 0.03 plus 0.12 is about 0.15 to the best of my math ability, give or take. Do I know if that's significant? Nothing in the model tells me. What I know is that size doesn't matter in public schools, and I know that there is no difference in how much size matters in private schools. So the model is telling me that the size slope is equivalent across the two schools, but it doesn't give me directly what it is in the private schools. So, but I can add these two together, and that's literally what happens next in the code. So question earlier about does these need to expand in terms of the number of fixed effects? Yes. So what this little piece of code is doing here, note this is contest 1D. That's what you use if you're trying to build a single slope as a linear combination of model parameters. So this means don't include the fixed intercept. Do include the slope for size. Don't include the main effect of public versus private because we're not talking about that now, we're talking about size. And for the interaction term, put a 1 there, meaning turn it on to be for private. If I had wanted it to stay for public, then it would stay 0. So it's the value of the moderator that goes in the last slot there. So you'll get a chance to practice that on your homework assignment, I believe. Yes. And then so for the F-test for the model, now that we have 3 terms to be added together, I have 3 sets of parentheses. So I'm saying lump together the 2 main effect slopes and the interaction slope in a 3 numerator degree of freedom test as to whether they're jointly different than 0. And that is 2. So in terms of effect sizes, now I have a function here that has base model and model 1, and then I have model 2. So I've had the capacity to designate a base model and then 2 alternative models so that you can track the R-square of each and the change. And so it does that. So in this case, here's a summary of what happened. The main effects of size and school type accounted for 23% of the random intercept variance. And then adding the interaction bumped that up just a tiny bit, but not enough to write home about. And the residual remains unexplained, as well it should, because none of these things are people things. And then here's the Wrights and Sturba version. They come up with a slightly higher number instead. And then total R-square increased as well. And here are some words. There. So at the end of all of my examples, you will see a results section that is illustrating how I would write these things up for publication purposes. These are usually longer and more detailed than what I would provide, but this is for more pedagogy to make sure that I use all the terminology and stuff. And so in terms of a structure, you'll note that there's always an opening paragraph that essentially is like my analytic strategy. So like what kind of model I used, what kind of software I used, any other kinds of choices, like how did I test this? So for instance, the significance of fixed effects was evaluated with univariate and multivariate wall tests with Satterthwaite degrees of freedom, whereas random effects was evaluated with likelihood ratio tests. So just procedural kinds of things. If you're going to do the same kinds of tests like over and over in your results section, just talk about it once. Likewise, I described how I did effect sizes in terms of specific how they were computed specifically. Then I've got the empty model, so the descriptive statistics about the intercepts that we've been talking about, and then in 1 paragraph each for the subsequent models. So no pictures in this example because the model's pretty straightforward, but we have some in the next one. So there, 136. I did it. Questions or comments or things you want to hear again? Sprite today. Too much caffeine already. No? We're feeling okay? Okay, feel like you can do this? We're going to find out, aren't we? So your TAs have been through homework in both packages. They are prepared to help you. They have verified the answers as well. It will be due next Wednesday instead of Monday. So since we finished this, we should be in good shape to do that. That means that next time we get to start lecture 3 and example 3 on person level predictors. That's my plan. How's that sound? Good? Okay, would you like 7 minutes of your life back then?
Yes, but when you're done, I have a quick question for you when we're officially over.
Sounds good. I will hang out in case folks want to talk to me, and otherwise I will let you go for now. So it's garbage day. Happy garbage day. That means I will see you Thursday, hopefully in person. We'll see. Assume as much unless you hear from me, okay? Bye for now. Thanks for being here.
Thank you, Lisa. That better.
Thank you.